So we've done mirrors. Now we're about to do lenses. So what is a lens? All a lens is a piece of curved, transparent material that operates based on index of refraction. So last time we saw that if you have light traveling from one medium into another, it gets bent. Remember that? So what are you actually seeing when you look through a lens? So here's a lens that someone put up by some text. So there's light coming off of the text, and it's going through the lens, and when it hits the air, it gets bent. And so what's coming at your eyes is the bent light, so your eye traces that back and sees the text at some other position. Right? So that's all that's happening when you look through a lens. So let's look at that in a little more detail. So a lens is just a piece of curved, transparent material. You're seeing, I'll write that down, curved, transparent material. And it operates on refraction. And what you're seeing here is you're seeing an image of the text. So just like with mirrors, there are two main questions we're going to ask. We're going to ask where the image is, and we're going to ask what kind of image it is. So the first thing to figure out is how does the transparent material bend a ray of light? So for these two things, so suppose you have a block of glass or something. So outside we have air, and this is glass. So the light is traveling through the air, and this light ray hits the glass at normal incidence. So what will happen to the ray? Will it be deflected? Did you remember Snell's law? N sine theta equals N2 sine theta 2. What's theta here? How do you measure this theta? Remember, if you have two materials, there's a normal, and you have something coming in at some angle to the normal, and then it gets refracted at some other angle, theta 2, relative to that normal. So what's the angle between this light ray and the normal? 0. So sine theta is going to be 0. So will it be bent? No. It's just going to go straight through. So it just goes straight through, and on the other side, it goes straight out. So that doesn't do anything. What if I have something coming in at some angle, theta I? Well, this is glass, so is the ray going to bend toward the normal or away? It's going to bend toward. So, whoops. So if it went straight through, it would go like that, but it's going to bend toward the normal, so it's going to be a little bit more like this. So this is going to be the refracted angle. And then over here, we have a new normal. The new normal. So this angle is theta r. So what is when the ray exits the material on this side, it's going from glass to air. Will it bend toward or away? It's going to bend away. And it's going to bend away at the same angle as the angle of incidence. Do you believe that? So this outgoing ray is parallel to the incoming ray. So this does not really act like a lens. All it does is shift all the rays a little bit, but it doesn't change anything. Because all the rays that come in on this side are going to go out at the same angle on this side. They're just going to be shifted down by a little bit. So that just moves the image over a little. So this doesn't bend rays. But let's look at this prism. So here you have air on the outside again and glass on the inside. And you have a ray coming in. It's going from air to glass, so it's going to bend toward the normal. So if it went straight through, I like to look at it upright, so I'm just going to turn my paper. Maybe it's really good that that thing didn't work today, because now you can see my ruler and everything. So it's going to bend toward the normal, so instead of going straight through, it's going to be a little bit more like this. And then I have to draw another normal over here that's perpendicular to the interface. And now I'm going from glass to air. So will it bend toward or away? It's going to bend away. So if it went straight through, it would be like this, but I have to bend it away. So it's going to be like that. So you can see that for the prism, the outgoing ray is bent from the incoming ray. Like, they're not at the same angle. These two were at the same angle. They were parallel. This ray and this ray are not parallel. So the prism bends the light. So this does bend the light. How did we get that? How did we get that? Well, you could do Snell's law here twice, and you could actually find the angle, but we know that it bends it, and we can figure out how much it bends it later. We'd have to do Snell's law twice. It looks more bent, doesn't it? Like this one is coming in, this one's coming in horizontal, and this one's leaving at some angle down. So those two things aren't parallel, right? No. Okay, so how do you actually make a lens? So let's talk about a converging lens. So you can start to get a converging lens by just taking a planar block and putting two prisms on the top and bottom. So if I have 3 parallel rays coming in to this thing, what will happen to them? The central one will just go straight through. What will happen to the one on the top? Yeah, it's going to come in, it's going to bend, and then bend again. And this one's going to come in, and it's going to bend, and it's going to bend again. And these 3 rays will focus right here. So if you want all the incoming rays to focus at this one point, you just have to make a curved surface so that you get all the parallel rays to focus at one point. So if you have parallel rays coming in like this, if we make a thin lens approximation, we can just pretend that they're all going to bend at the center. So let's draw a dashed line down the center of the lens. And you just say, okay, they're all going to bend at the center. And all of those lines are going to go straight through the focal point. So that's only true for if the incoming rays are parallel. If they're not parallel, they'll focus somewhere else. And we're going to treat rays, for all these lenses, we're going to treat the rays as bending at the center line. So light rays are reversible, though. So if I send a ray in like this and it goes through the focus, I could just reverse it at the focus and send it backward. If I send it backward, how will it emerge? It's going to emerge parallel. So if I take all these rays and start them from the focus, and they come up to the lens, when they get bent, so this one's going to go straight through. When they get bent, they're going to come out parallel. Whoops, oh dear. So they come out parallel. Other questions about that? Okay, so I have a converging lens. I have a converging lens made of glass. What do you think will happen to the focal length if I submerge it underwater? So where the index of refraction is greater. I want you guys to take a second, talk about it with the person next to you. Do you think that the focal length will get shorter? Will it stay the same? Or will it get longer? And think about the principle upon which the bending of the light rays is occurring. So take 30 seconds to make a prediction. Okay, what do you guys think? Who thinks it will get shorter? Who thinks it will stay the same? Who thinks it will get longer? Yeah, it will get longer. Why will it get longer? So, what's that? Yeah, n is greater. So the bigger difference you have between the material around the lens and the lens itself, the bigger difference in n between those two things, the more dramatically the rays bend. So when you submerge the lens in water, the difference between the n of the water and the n of the lens is now not as great. Those two things are more similar than lens and air. So stuff's not going to bend as dramatically, which means that the focal length is going to get longer. So rays will be coming in like this, and then the difference in index of refraction between the two things isn't as great, so the things aren't bent as much, so it's going to end up somewhere over here. Does that make sense? So they're going to get longer. So then one thing to note is that if the parallel rays, if rays are coming in parallel but they're not aligned with the optical axis, like this picture, okay. We just aren't meant to have class today, that's all. Blech. How's that? Is that okay? Okay, if they come in at some other angle, they still get focused, but they get focused on the focal plane. This is why you see Arlo the other way. Like why when you look in the mirror, you see, actually, never mind, that's not why it is at all. I don't know what my brain is doing. Forget it, I didn't say that. Moving on. We define the focusing power of a lens as 1 over the focal length. So if you go to the optometrist, they give this in units of diopters, which are meters to the -1, so inverse meters. And we'll talk more about optometry in a little bit. But let's start with doing some ray tracing for converging lenses. So this is a lot like what we did for mirrors, except the rules are a little bit different. So let's do this one. So you guys can try it. This is good. So there are still 3 principal rays. So here's the object. There's the central ray, goes straight through the center of the lens. Let's do that one together. So straight through the center of the lens. So I line up the tip of the arrow with the center of the lens, and I draw a line straight through. So something like this. So that is the central ray. And now I want you guys to draw the parallel ray and the focal ray. And see if you can figure out where the image is. So the parallel ray is going to go in parallel to the optical axis. So like this. Oh dear, color. And then it's going to go through the far focus. So this is the parallel ray. And then finally, we have the focal ray. So that goes through the near focus to the lens, and then it goes out parallel. So they're all converging right here. So the image is right there. And this is the focal ray. Okay, so we're going to come back to this in a minute. But what do all converging lenses have in common? So these are all examples of converging lenses. What's true about all of them? What? What's true about all of them? Yeah. They're all bigger in the middle also, right? Like the width in the middle is bigger than the width at the top. So they're thinner at the edges is another way to say it. That's how I'm gonna talk about myself from now on. All right. Any questions about that? Okay, let's try it for a diverging lens then. So a diverging lens is one where if you have parallel rays coming in, they'll be deflected away. Yeah. Yes, we could do. I was gonna come back, but let's do it. Right. We can do it right now. So if we want to characterize this image, is it real or virtual? It's real because the rays are actually converging. Is it upright or inverted? It's inverted. And is it enlarged or reduced? I think it's the same. Yep, so it's the same. Okay. Any other questions? All right, why don't you guys try the diverging lens. The diverging lens, I think, is the trickiest of all. But see if you can follow the instructions for the three principal rays. And if an image isn't formed, try tracing back the rays. Hint. Okay, so let's start with the central ray. That's the easiest one. So the central ray starts at the tip of the arrow, and it just goes straight through the center of the lens. So this is the central ray. The parallel ray goes in parallel to the axis. And then it's deflected away from the near focus. So I line the ruler up like that and make that ray go away. So you can always think about, like, it's a lens. The light's always going to go through. It's not going to get reflected like a mirror, right? So use that thought when you're thinking about it, because you might have thought, like, oh, it's going to go through this focus, or it's going to go back this way or something. But it always has to keep going through, because it's a lens. It's transparent. So this is the parallel ray. And then finally, we have the focal ray. So the focal ray heads toward the far focus. So that's the one on the opposite side from the object. So it's going to head toward that. And then at the central line of the lens, it's going to emerge parallel to the optical axis. So it's going to go out like this. Okay, so where is the image? So these things, so if you're an eyeball over here, I like how you're never a person with an eyeball, you're just always an eyeball. That's good. You see these rays coming at you. So where does it look to your eyeball like they came from? Behind the lens. Right, so we have to trace them back. So let's trace this one back. It's going to go like this. The focal ray is going to go back like this. And the central ray was already there. So the image is right here. So characterize it for me. Real or virtual? Virtual, because those rays aren't actually converging at that point. Upright or inverted? Upright and reduced. Good. So what is common about all of these? What's the same about all of these? They're thinner in the middle. Okay. What was your question?
Will we ever have two rays actually converging but not a third?
Will you ever have two rays converging? No. The three rays will always come together if they're going to come together. And in fact, all the rays, remember, an object is giving off an infinite number of rays. And if you drew them all, they would all come back to that point. But we're just drawing three principal rays because an infinite number would be rather tedious. I know, I'm hilarious. So it's thicker at the edges. Okay, so you can also do this with math, and the math is almost exactly the same. So in fact, everything is the same. The only difference is, remember how the focal length depended on which type of mirror you have, whether you had a concave or a convex? Here, the focal length depends on which kind of lens you have. So you have a positive focal length if your lens is a converging lens. And you have a negative sign for your focal length if it's a diverging lens. So this is the only difference between this and the mirrors. So let's go back and do the math. So let's go back to activity 7. So here, we're going to use that equation again. So it's, I want to use blue. It's 1 over f equals 1 over do plus 1 over di. What is the value of the focal length here? Let's have numbers. So let's make this 1 and this 2. So this is a distance of 1 and this is a distance of 2. So what's the focal length? Is it plus or minus 1? It's plus 1 because it's a converging lens. And what is the object distance? The object is 2 units from the lens, so this is 2. And it's a real object. So if we plug those things into the equation, 1 over 1 is 1, 1 over 2 is a half, plus 1 over di. So that means that di must be plus 2. So the plus tells you what about the image? It tells you that it's real. And the 2 tells you it's 2 units from the lens, which is what we got with the ray tracing. So let's do the magnification now. So m is still minus image distance over object distance. So that's going to give us negative 2 over 2, which is minus 1. So the 1 tells us that it's the same size. And the negative sign tells us that it's inverted. Okay, any questions on that? Will you guys try it for activity 8? Yeah. Where, oh, good question. So she said, where would the eye be when you're looking at this image? So the eye has to be over here. If you're, okay. Oh dear. Oh. The eye has to be, I felt like I was going crazy while I was preparing for this lecture, and I still feel crazy. Do you know how many songs are about mirrors? Like pop songs? Like Justin Timberlake has been my buddy for a couple days now, which is weird. The eye has to be over here. If the eye was between the image and the lens, like the eye only sees rays, so these rays have a direction, right? They're coming this way. So if you were an eyeball in here and you looked this way, if you looked toward the image, your head would block the rays. You would be between, actually, I have a lens here. Let's do this, actually. So this is a converging lens. And here I have a rubber ducky, which is going to be our object. Rubber duck, more songs, okay. Does Sesame Street still exist? It does? Is it terrible now? It's not? But it was like so good when you guys were young, right? Or when I was young, it was good. All right, so let's illuminate our object, rubber ducky. If we do this for too long, he starts to melt. So here's the duck. This is a converging lens. So the light rays are coming off the duck, and they are coming to the converging lens. And then the lens starts bringing them together. Can I put it up there? I can't, but you'll be able to see what I'm going to do next. So I have this screen, right? The converging lens is going to create a real image for us, somewhere over there. And the real image means that the light rays actually converge there. So if I put a screen there, we'll actually see something. If it was a virtual image and you put a screen where the virtual image was, you would not see anything because there aren't light rays actually converging there. So there you can kind of tell there's something yellow, right? So there's the duck. So this is exactly the same principle as how the projector screen works. There's a big bulb back there that's projecting onto the screen, and so there's an image focused on the screen, and you can see it. Same idea with the duck. I should have turned the lights off for this, but Alan's not here. What do you expect? Okay? What was the question? Now, what was the question? I can't remember. Tell me the question again. Where was the eye? Oh, right. Yeah, so the eye, so if I come over here, I will eventually, I'll see the image of the duck. I don't want to blind myself much. But if I put my eye in here, and I tried to look at the image of the duck, I can't see it because now my head's blocking out the light. Like the rays aren't coming this way, they're coming that way. So my eye has to be able to intercept those things. It looks wet. All right. Okay, so what were we doing? Oh, we were going to try, are there any other questions? Yes.
Near and far focal points, that's relative to the object.
Yeah, that's a great question. The near and far focal points are relative to the object. So if the object, the focal spot that's on the same side as the object is the near focus, and the one on the opposite side is the far focus. Okay, so I'd like you guys to try doing the math for the diverging lens real quick. Oh, you want units? Jeez. All right. Let's make this a 1, and let's make this a 2. So that means this is also a 1. It's going to be -1. Why is it negative? Because it's this kind. It's because it's the diverging kind. And the focus is a distance of 1 from the lens. So what's the object distance? The object is 2 away from the lens, and it's a real object, so that's going to be 2. So if we plug those into the equation, 1 over -1 is -1. 1 over 2, there's a half, plus 1 over di. So if I subtract a half from both sides, I'm going to get -3/2 equals 1 over di. So di is -2/3. So the negative sign, again, tells me that this is virtual. And it says that it's located 2/3 of the way away from the 2/3 units away from the center, which this looks like approximately 2/3, right? Yep. So that seems like we did that right. So then for the magnification, that's still minus di over do. Di is minus 2/3. What's do? Do is 2, so there's a 2 in the denominator here. So that gives us, oh, and I need another negative sign, right? Negative that, which is 1/3. So it's positive 1/3. So this means it's reduced, because 1/3 is less than 1. And the positive sign tells us that it's upright. So we got the same thing. Yay, question. Why is the object distance positive? Oh, the object is real. We haven't even seen a virtual object yet. But it's coming. Any other questions? Okay, no more questions. You know what that means? Are you getting it? All right. Let's see if you're getting it.